So in this short section, I want to talk about two of Newton's laws of motion. His first one is this is Newton's first law, is basically, I'll paraphrase, if an object is at rest, it will stay at rest until it's acted upon by some outside force. Okay, and an object in motion will stay in that same motion with the same speed and direction unless acted upon by some outside force. Okay, so that's Newton's first law. Newton's second law, if you had to put it on a test, hint, hint, if you simply write force is equal to mass times acceleration, I would be fine with that. Let me bring up my little drawer. Okay, you probably heard this before. Force is equal to mass times acceleration. Where force is a capital F, mass is a lowercase m, and acceleration is a lowercase a. So now here's the deal. This is how this works. Let's say that you observe some acceleration, okay, and you know its mass. We're going to see that there's a difference between mass and weight. Mass, you know how much matter that object has. Can you see where you can understand or calculate the force? Okay. So that's kind of, we have three variables here, force, mass, and acceleration. Alternatively, if you know or understand the force, say you know this one, you know the force, and you know the mass, okay, we can calculate the acceleration or predict the acceleration with that force applied to that mass. Okay, so it's kind of cool. Put another way, okay, I'll put it up here. F is equal to mass times acceleration. If something accelerates, there must be some sort of force behind it. If something accelerates, that force must have been applied. And here's a kind of a simple way of getting back and forth between observed acceleration and the force acting in the background, or the force acting in the background and the anticipated acceleration. Okay. So with that in mind, let's look at dropping objects. I should find something that I can drop and it won't get hurt. So here's a pen. I can drop this pen, okay, to the floor. You're going to hear it hit. Okay, we knew that was going to happen. And like this slide's going to tell you, I could tell you how fast that object was moving. Okay, I know it, let's see, it probably take 1,001, maybe 2 seconds to drop to the floor. Okay, the first second that it fell, at the end of the first second, it was going 10 meters per second, or 9.8 meters per second. Okay, if it was far enough before it hit the ground and it was going to fall another 2 seconds, it would have been going 10 plus 10 or 20 meters per second. Okay, we know how fast objects we know the behavior of objects as they fall. Due to, if I were to ask you why it's falling, because of the force of gravity. Okay, we're going to talk more about this universal law of gravitation here in a minute, but it's gravity. Basically, there's an interaction between this pen and the center of the Earth. Okay, and we have this sort of acceleration going on because of that force of gravity. The little green guy on top of be careful, little green guy on top of the building there, okay? So when he drops an object, now here's one thing about it. I'm going to try to convince you of this. And Galileo convinced himself of this, apparently by dropping objects off of the Leaning Tower of Pisa. I don't know if it was leaning at that time, okay? But he dropped objects from way, way high. And independent of the mass of that object, okay, or the weight of that object, independent of that, they accelerate at the same rate. Isn't that awesome? Okay, so regardless of the yellow thing that he's dropping over the edge there, kind of reminds me of David Letterman, wasn't it? He used to drop things off of buildings. I don't know. Anyway, like I told you, when I dropped that green pen, if we were to be able to let 1 second fly and to gauge how fast it was going at that moment in time, 1 second after I released it, it would be about 10 meters per second. Now, I need to qualify this. This is assuming there is no air resistance. having an issue with regard to the object I'm dropping. So this is actually assuming no air resistance, which you really can't assume that on Earth, but we got to fix to that too. So without ignoring the resistance of air, so the slide says after 1 second, it's going a velocity or a speed of 10 meters per second straight down. You allow 1 more second, and you can see that actually now it's going 10 plus 10 or 20 meters per second. So if I were to query you this, do you see, and it looks like we're going to need more room down here because it's going to splat, but if it were allowed to go to 3 seconds, okay, can you see where the velocity would be, 30 meters per second? Okay, that is the acceleration due to the force of gravity, and it works regardless of mass. Isn't that awesome? So I've rounded it to 10 meters per second. Notice acceleration is meters per second, how you're changing the speed per every second you allow that change to occur. Okay, I should say meters per second, how you're changing the velocity. Okay, so pretty cool, pretty cool. So I mentioned that dropping two objects with different masses, they will go faster and faster and faster, accelerate as they are pulled to the center of the Earth, the force of gravity, and they should hit the ground at the same time. And this one, I don't think I'm going to click it because it would take too long. But there's a YouTube video out there, Apollo, let me make sure I get it right, Apollo 15, when they were on the moon. What this video would show you is the astronaut has a hammer and the astronaut has a feather. And he basically prefaces before he drops it, says, "This is to test whether Newton was right." I think it was Newton. No, I think he refers to Galileo. Galileo did this on Earth. See if, without air resistance, these two objects, the hammer and the feather, will hit the ground at the same time. And of course they do. Okay, so on the moon, we also have a gravitational force. It's about 1/6 that of Earth because the mass of the moon is significantly less than that of the Earth. But that force will accelerate objects slower, okay, than our 9.8, but they will fall regardless, at the same rate, regardless of their mass. So that's pretty cool. So we've been alluding to this pull, this attraction of gravity between objects. And so when I drop a pen, that actually is this gravitational forces between the pen and the center of the Earth. But here, kind of turning it sideways, any two masses have a gravitational attraction to each other. And so that gravitational attraction to each other is shown in blue arrows here. So I'm going to show you, kind of start to reveal down here the FG, this thing. This is the force of gravity. Force of gravity. And this is gravitational. This is a constant. I'll just put constant. We have a lot of constants in physical science associated with this universe, how this universe behaves. So that's the gravitational, that constant. Okay. So the M1 and M2 are, that would vary depending upon the mass of your green one and the mass of your gold one. So, but do you see how, and this is pretty intuitive, that attraction would increase if you increase either one of these masses, okay? So we're going to put actually the product or multiply M1 times M2 in the top. Okay, down there on the bottom, I don't know if you see this D squared term. So D is distance. What distance are we talking about? Well, the distance between the two objects of interest here. So notice that, and if I were to ask you before I revealed this, what happens if we take the green and the gold and try to separate them? And you probably would say, well, I bet the force will weaken, and it does. Okay, and actually this says it will weaken according to the distance squared, or it will increase according to the distance squared. I think that's how I'm going to think of that. So anytime you see like an equation like this, and you have one variable, what we say in the denominator, that actually must have what we say is an inverse relationship to the thing that's on the other side. So basically then, as distance goes up, okay, force goes down. Okay, as distance goes down, force goes up. They have an inverse relationship. Here, talking about up here with regard to the masses, and we talk about kind of relationships between variables like this a lot, kind of the indirect relationship or the direct relationship. So this says basically if you increase the mass of either one, the green or the gold, you're going to increase the force of gravity. So these have a direct relationship.